Yeah, go away. 100%.
Jacob did too.
Huh?
Jacob did too.
Jacob, you got 100%? I had it
You're
right,
both
but I
bogus
second
for that.
guessed myself.
Brinkelhoff, you guys. All right, solutions and mixtures.
I don't want to talk about it.
Ben, I showed you my scores.
Most of you missed that on the quiz. Calculating your molecular mass of hydrogen and
No, I'll just pay attention. Other than multiple choice? Right. I only got the chart wrong and I had the right answer. I second guessed myself. I felt like I needed to do
all right, here we go. I am starting notes. Solutions come in the form of solids, liquids, and gases whose macroscopic properties do not vary. That is due to the fact that the solution's composition is uniform throughout. Remember, we've talked about molarity. Molarity is the capital M. We also talked in regular chem and honors chem about molality. We don't do molality in AP. We only do molarity and mole fractions. So molarity, remember, is moles of your solute divided by liters of the solution. So the entire solution. This has to be in liters. If you've done measurement in milliliters, you must convert it into liters. So for example, 75 milliliters would equal, we move the decimal point 3 spots over, 0.075 liters. For liquid solutions, the solute may be a gas, like in pop. You've got gas dissolved in there. That's your CO2 gas dissolved in a liquid. It may be a liquid dissolved, or it may be a solid, kind of like Kool-Aid or sugar in the mix. While there are different methods for describing solution concentration, molarity is the most common concentration that we use in the laboratory. Now, if you are in industry, sometimes industry, like I said, will use molality because they've got big temperature differences. So for example, if you're at a chemical plant and most of your stuff is done outdoors and you're in an area of the country where the temperature fluctuates greatly, like here, it can fluctuate here from almost 100 degrees to negative 20 during the winter. That's a big fluctuation that can change the volume of your material. So at that point, you wouldn't necessarily want to use liters down here because you wouldn't be very consistent. That's where they use molality. Molality deals with kilograms of, I think it's kilograms of solute over, yeah, I'd have to look it up. But anyway, it doesn't have volume in it. Okay. All right. Why are you not letting me advance? Properties of liquid solutions. The components, now these are two liquids mixed together. So let's say that I have like isopropyl alcohol, rubbing alcohol, and water. Okay. Those are two liquids mixed together. Sorry. I would not be able to filter that because they're both liquids. Everything would just go through the filter paper. There's no components large enough to scatter visible light. So the Tyndall effect, you guys know the Tyndall effect? Know the Tyndall effect? Okay. So the Tyndall effect will tell you if you are dealing with a colloid or if you are dealing with a suspension. So I'm trying to find some pictures here for him. That's refraction.
What is this colloid and suspension?
I'm trying to find, just give me a second to get my crap. Not on here. Drive. There's drive. back my drive. Chemistry. Here we go. Okay. So when we're looking at different mixtures, okay, we have different classifications. There's heterogeneous mixtures, which is your suspension and your colloid. So kind of think of this as like a snow globe, okay? You shake it up, it's suspended there, but over time it settles back down, okay? Colloids then have slightly smaller pieces, so they tend to stay suspended in there, but they will show the Tyndall effect. And you've seen this before, like in the morning where you've seen like sun shining through and you get kind of this refraction of light through there. This is also fog, for example, is a colloid. That's why they tell you not to use your brights when you have fog, because it'll refract the light back into your eyes, or reflect the light back into your eyes. So the Tyndall effect, when you shine a light through it, if it's a solution, it'll go straight through. If it's a solute, if it's a colloid, or if it's a suspension that has just been shaken and hasn't had time to settle, it'll also show positive for the Tyndall effect. So when you look at these different items here, your solutions, really the difference between these is the particle sizes, okay? So typically a solution is going to have very, very tiny particles, like on the order of 10 times or 1 times 10 to the negative 7th centimeters. So that's really tiny particles. You can't see those with your eye. When you look at the colloid particles, they're between there. And so they stay mixed together. They're just bigger particles. So they end up reflecting that light back out. If you're talking about suspensions, though, it's 1 times 10 to the negative 5 or larger. So this could be like a tossed salad. Like you can see the parts of a tossed salad, or trail mix or something like that, okay? This is also sand and water. So the grains of sand are big enough that they're just going to go right to the bottom. So this is what a suspension looks like. And this is truly the difference between a solution and a colloid and a suspension. This is like sand and water, or the snow globe, or orange juice with pulp in it. This is like jello or fog. You can't see the individual water molecules that make up that fog, okay? But they're there. And then this would be your true solutions like Kool-Aid and iced tea and stuff like that. Did that help at all, I hope?
Yeah.
Okay. All right, getting back over to here. So that's the Tyndall effect. In order to separate a two liquids that are in a solution, you would need to do one of two things. Well, there's probably a couple other things, but these are the ones that we're going to talk about. You can end up using distillation. So do I have a picture for that? I do not. Let me get back to this slideshow over here for regular chem. Did I close that out? I shouldn't have closed that out. That should be here. Why is this not coming up? It's over here. That's why. Okay. So distillation, for example, looks like this. Okay. If this wasn't salt water, let's say that this was rubbing alcohol and water in here instead of salt water. You would heat this up, but you wouldn't heat it up to 100 degrees Celsius. Okay. Let's say that, I don't know what the boiling point of alcohol is, but let's say that it's 75 degrees Celsius. You'd heat this up to 75 degrees Celsius. That alcohol would change into a gas. Gases are less dense, so it's going to rise. Then it would come down over here. You've got a tube within a tube here, essentially. The outside tube has cold water running through it. They don't mix. That's going to cool that gas that's coming along here down. And then you could collect that as a liquid over here. So you would end up collecting the rubbing alcohol over here, and then your water would stay over here because it wouldn't have boiled away. So you're taking advantage of two different boiling points in that process. Another way of doing this is chromatography. And if I have enough time today, I'm hopefully going to be able to get to that discussion. Okay. And then chromatography is, you guys have probably seen that before. It looks like this. Okay. A lot of times in elementary, middle school, they'll do stuff with like Skittles or M&Ms where you rub it on there and then put it in water and then you see the dyes move up. Those are liquid dyes. And the difference between, well, we'll talk about that. We'll talk about how that works. It's just one of the ways to make it happen. Okay. So that's chromatography. Ion concentration then. Ionic compounds typically will dissociate into ions when they form solutions, but not everything does this. So that leads us to a conversation about solubility. Okay. Some things, some molecules are more attracted to the water than they are to the other thing that they were in with. Okay. So for example, when we have like AgCl, okay, the Ag and the Cl are more strongly attracted to one another than they are the water. So this stays together. This is called insoluble because the attraction between these is stronger than the attraction between here. So the water will not pull this apart, and therefore AgCl is considered insoluble in water. Other things, though, the attraction of the water is greater, so it's going to pull that apart, and the water will then surround those ions. Remember, the positive end of the water will be attracted to the negative ion, and the negative end of the water will be attracted to the cation. Make sense? Okay. Composition of solutions then. We saw in Unit 1 how the composition of a solution can be expressed in terms of moles of the solute per liter of solution. That is known as molarity. In relatively low molarity solutions, there are small numbers of solute particles compared to solvent. In high molarity solutions, there's large numbers of solute compared to the solvent particles. You could end up with a situation, one of two situations. You could end up with more solute than you have water. And in that case, this would be a saturated solution. Or you could end up with less solute than water, and that would be unsaturated. In other words, if we go back to this diagram, we have extra water molecules out here. Do you see these floating around? They're not around anything. So that's going to be what kind of situation here? Unsaturated. Yes, Matthew.
What is saturated and unsaturated?
So unsaturated means that we have the extra water molecules left over.
So it's like when there's too much stuff in there that you can't take anymore.
Right. If you've used up all you have all of these surrounded here and you've got extras of these left over, that would be saturated. Okay. But in this case, we've got extra waters. This guy isn't surrounding anything. So we've got extra waters. We could add more ions in here and have water to be able to surround it because these guys aren't doing anything. They're just hanging out. So this guy would be an unsaturated solution here. That makes sense?
Yeah.
What about super saturated?
Yeah, that's a weird one. We're not getting into that. Don't confuse him with that. Okay, you guys caught up? You ready to go? All right. You will be asked to explain this process right here in a lab And I would almost guarantee in some fashion, you're going to be asked about how to do a dilution on the AP exam. I'd almost put money on it. It happens almost every year. Okay. So when you're doing a dilution, your solutions are prepared by adding water to more concentrated situations. So for example, when I get acid in, if I get in HCl, when I order this in, I order in 12 molar HCl. Okay. What does that mean? That means that I have 12 moles of HCl for every liter of solution. Okay. Now, rarely, very, very rarely do we use it in this concentration. But the nice thing about ordering this in with this concentration is I can dilute that guy down to any level I want. Yep, you did. You did a serial dilution lab. Okay. Remember that? Everybody, we had the blue thing lined up here. Okay. And you're going to end up diluting stuff this year too as your part of your Beers Law lab.
The 3-day one?
Yep. All right. So first of all, you're going to calculate the number of moles present in the final diluted solution by applying moles equals concentration times volume. So if we do molarity equals moles over volume, and now we want to know moles, all you have to do is multiply these two things together. That's what this is saying. So calculate the volume of the starting more concentrated solution that supplies the moles of solution. That moles equals concentration times volume. So the volume of the water must be added to the concentrated solution is simply the difference between those. So we talked about M1V1 equals M2V2, okay, where we take the molarity. This is going to be, if I know that I'm starting out with 12 molar here, for example, I need to know how much volume I'm going to need for this. What do you guys want to make this less than 12? What do you want to make it? 6 molar, okay. And this is how much we want to make. So how much of the 6 molar do we want to make? How many? 4 milliliters? Okay. I don't know that I've got 4 milliliter volumetric flask. I think the smallest I have is 25. So I'm going to do 25. Okay. So 25 milliliters here.
12.5.
Okay. So now we are going to solve. I'm trying to move this thing out of the way. We're going to solve for how many milliliters of this I need. Now this M1V1 equals M2V2, you can keep this in milliliters. If you're doing molarity, it has to be in liters. You don't have a choice. But yep. Okay. So I'm going to multiply these two together, and then I'm going to divide by 12. I think it's 150 divided by, 12. So I would need 12.5 milliliters of 12 molar HCl. I'm going to measure that using, if we really, really, really wanted to get it highly accurate, if they gave us an option of being able to use a burette, that's what we would want to use. If they give you that option, use it. Okay. So I would use a burette to measure this with. Then I would put that in what? You guys remember what you put it in? Volumetric flask, right? Okay. We're going to put it in the volumetric flask. So this goes into, we measure this. Measure using burette. Okay. And then put in to a volumetric flask. What's our next step?
Third.
Mm-mm.
Do you have to have like a base or an acid or something?
We're diluting it down. What do we dilute with?
Add water.
Yep, add water until then. When?
You get the color you want.
Reaches the etched line, right.
Oh my goodness.
Add the water until
The ink becomes right.
the meniscus
I'm writing this down.
reaches the etched line. Now what do we do?
Do we stir it?
Then we stir. And you're done. They will typically give you a list of equipment and say, here's the equipment that you have on hand. Tell us how to make this happen. You want to pick the most accurate piece of equipment that they have given you. Yes, Matthew.
We're doing this lab later though, right?
Yeah, I think it's like the beginning of
It's
not
next
next
week.
week, but the week after, isn't it?
No, I think it's all next week.
Is
It's
it all
Monday,
next week?
Tuesday, Wednesday next week.
Okay.
Because
So
we're
we
all
don't have to
Thursday,
write this
Friday.
down.
Okay.
Hardwood.
We're gonna keep doing it.
We might be smart to have in your notes.
Yeah, because this is gonna be the question we're probably thinking on.
It'll probably be one of the FRQs on it. I think that's
Yeah.
what we tried to say.
Yeah. The thing
We good? Anybody still writing?
I'm good.
All right. So this is what I was talking about. These are other examples of this. Here we are looking at, yep, we've got a stock solution here. It's 8 moles, molar. We know that we want, you can end up doing it this way or you can do it my way. I think my way is easier, but this is another option if you want to look at the way they did this.
What's your
M1V1 equals M2V2. Okay. So this is kind of how to use some of that equipment. You guys can look through this. It's pretty much what I just went through as far as how to get things done. This is what a burette looks like. Remember that guy, the really tall, long, tubey looking things. This is your volumetric flask. Remember, your volumetric flask can only measure one volume. That's
Does
it.
it have labeled acid and base on each side, right? On a burette?
No, that's over here. That's on this thing.
Yeah.
Yeah, for the bread.
Yeah. And then you put
It's
base
just
on
the
one
clamp.
side and then
Well,
acid.
that's a titration, hun. That's different. This is just, you could use this to measure out your solution. A burette is much more accurate at measuring out than a graduated cylinder. So if they give you an option between a graduated cylinder and a burette, pick the burette. Okay. You want to pick the piece of equipment that is the most accurate or most precise. Remember also that, let's say with this this guy that we needed to add 66 milliliters of HCl to this. Okay. So this is 1,000 milliliter beaker or volumetric flask. The mistake that a lot of people make when they're doing this is they'll go 1,000 minus 66. Let's see where that is. 34. I need to add 934 milliliters of water.
What?
Please.
Why would you think that?
Okay.
Fill it all the way
Yep. So they take the 1,000 here and they'll subtract the 66 from here and they'll go, oh, the remaining is the water. Don't do that. Okay. I've showed, if you were in regular chem, I showed you a video where if you mix two liquids together, they don't always result in the combined volume. They actually are less because that volume of mixing When you mix those together, they end up being less than this. So if you mix 934 mils of water in with this, you may not end up with 1,000 here. Okay, you may end up with 950. So don't do this. Okay, you add your 66 mils of HCl and you fill up until the meniscus reaches the etched line with water. Okay, do not make that mistake. It happens every year. Every year that happens. Don't do it.
I'm gonna do it.
All right. When you are dealing with diluting acids or bases, this is a very, very exothermic process. Oftentimes, you will get a lot of steam and energy out of this. It can be dangerous, okay? I always do this under the hood with the hood on, pulling the air out. I made the mistake my first year here, trying to dilute it in the back room while somebody was teaching in here. I'm like, oh, I'll just get this done on my prep period. It was not good. I had to like walk away. I couldn't. The fumes were so bad. Okay. So always do it under the hood. Typically, if we're doing like our sulfuric acid comes in at 18 molar. When we're diluting that down, I actually go and get ice from the training room and do it in an ice bath because it can get so hot that it'll crack my glassware. Okay.
Cool.
So these can be very, very dangerous diluting them down. You got to be really careful with it. All right. Here, we have to calculate the volume of lithium chloride solution that can be made with 13.3 grams of lithium chloride. So we want to make a 1.25 molar solution. So 1.25 equals, I've got to figure out moles, and then we're solving for liters. Okay, so I need to take 13.3 and I need to divide that by what? First of all, you got to know the formula for lithium chloride. LiCl. Okay, so I need a lithium and I need a chlorine. So that's 4, carry the 1, 2, carry the 1. So there is my molar mass for lithium chloride.
Quick, someone do it in their calculator.
And this is my grams up here. So those are going to cancel out, leaving me with moles.
0.314.
0.314.
Yes.
Okay, that's my moles of lithium chloride. Now I need to get this where I can solve for X. So X is going to equal what? It's going to be on top. 0.314 moles over 1.25 moles per liter. So moles cancel out, leaves us with liters. So I ended up with 0.2512 liters, or that would be 251.2 milliliters.
Cool. Okay.
And either one of these would be acceptable. I personally would leave it here. If you mess this up, if you try to prove how smart you are, that you can figure out that this is, and you mess this up, then they'll just mark it wrong. Okay. The other thing that I need to mention to you guys is when we are doing these calculations, if you don't box in your answer when you are done, they will take whatever value is in the lower right-hand corner. That is your answer. That's considered your answer. Okay.
Cool. Okay.
All right. What concentration in the solution could be made by what would be the concentration of the chloride ions in the solution that is made by dissolving 10 grams of zinc?
It's from the lithium chloride.
Oh, it goes along with the other question.
Yeah.
Oh,
Because
so
the
then
chloride's
you
a
use.
-1.
And
No,
zinc is a
positive.
positive 2. 3.7.
Not go in the
Not even have a source.
Here we go.
oh,
10 grams. Where did they get 10 grams?
By dissolving 10 grams.
I don't really know. I'm gonna be honest
Oh,
here.
I didn't finish this. I didn't
Writing?
finish this question out. Yeah, something got cut off. Okay. That's
No
good.
period.
That makes me feel better because I was feeling kind of stupid there. So this was zinc chloride, and that is ZnCl2 in a solution
Oh dang, there's a lot more.
that has a final volume of 500 milliliters. All right, that feels better.
Okay, so then you just do the
All right, yep.
stuff in.
So remember that I am going to have for zinc chloride, right? What is the concentration? So we're trying to figure out, we got 10 grams of ZnCl2. I've got to figure out, first of all, moles of ZnCl2.
65.
Okay, so this is going to be 136.3, and this is 1. And then for every 1 mole of ZnCl2, I have how many moles of Cl minus? Yep, 2 moles of Cl minus. Okay, so if I divide this and then multiply by 2, I'm going to end up with 0.147 moles of Cl minus. Then I need to divide this by what?
1,000. Oh, 0.5. Sorry.
0.5
I thought we were looking at a different thing.
liters. And that ends up being
Okay. Yep.
well, that was fun once we figured it out. I'm going to skip the we do
Okay. You got stuff.
because I want to see if I can cram in 3.8 here. Yeah, I got 8 minutes.
Solution.
All right, representation of solution here. Remember for the we do, when you do that, there's videos there that you can scan the QR code and they'll take you through how to do those. Okay, intermolecular forces come down to whether you're going to form a solution or not. Okay, when we talk about these items here, these are nonpolar items. So the attraction between them is going to be nonpolar. Okay, these are just going to be LDF. Here, you've got dipole here and a dipole here. So that means that those dipoles are going to be interacting. And then here, you're going to have hydrogen bonding. In this case, you're going to have ion dipole. And notice that if this is a cation or a positive ion, the negative part of that water is going to be what's attracted to this. You are going to have questions that are going to come up that end up having you draw this. You have to have the water oriented correctly with that ion. Intermolecular forces then exist between the solute and the solvent. Depending on the particular solute solvent, these intermolecular forces may either promote or prevent the formation of a solution. This is why when we talk about things mixing together, you will oftentimes hear something like dissolves like. Do not use that on an exam. They do not like to hear that. Okay.
It's just
You have to talk about how these things are related to one another. Okay. Polar solvents dissolve polar solutes because the attractive forces are there. Oil and water don't mix because one is polar and one is nonpolar. There is no attraction. The thing is that when you are talking about these things and whether they mix or not, I'm going to move to this so I have a little, no, I still don't have any room to draw. Here, I'm going to draw here. Okay. When you're talking about a nonpolar liquid and a polar liquid, okay, the polar liquid, like water, is going to be attracted to the other polar liquid, and it's not going to let this nonpolar in. There's too great of an attraction between these molecules, and it's not going to let this guy in. That is why oil and water don't mix, because the water is too attracted to another water molecule to let the nonpolar oil in. There's not enough of an attraction for this to get in there. Does that make sense? Where was I at up here? So we talked about that guy. Miscibility then is the ability of two substances to mix without separating. Solution will form if the solvent-solute interactions is stronger than the solvent-solvent and solute-solute. So like I was saying, with AgCl, the Ag and the Cl are so attracted to one another that the water isn't going to be able to pull that apart. There's not enough of attraction there. Okay. If, however, you've got something like NaCl, now that water is going to attract this guy, and he's going to get surrounded, and water will attract that guy, and that's going to get surrounded, and that's why that one's soluble. Okay. Again, make sure when you're doing your diagrams, you want to make sure that you have the right relative amounts of solute dissolved in the solution. You want to talk about how when you're doing particulate, you want to make sure that you have the ratios right. So for example, if you had this guy drawn in, you would want one of these for every two of these drawn in. These are not in a 1-to-1 ratio. So when you draw this, make sure that you have those ratios correct.
Yeah. Okay. I do. Okay.
So here, for example, this is a 0.2 molar KCl. This is a 0.1 molar. This is going to have twice as much as this guy. So if they ask you to, if they show you a diagram of this and say, draw what this looks like, make sure that you double the amount up there. More concentrated solutions have more solute in them. All right. Which solvent would be most effective in dissolving the following solutes, hexane or water? Identify the dominant intermolecular forces between and draw the particulate diagram showing this. Okay, so ethanol is going to be drawn like this. What is this right here? This is going to have a hydrogen bonding, right? Okay. So this has LDF always, dipole-dipole, and hydrogen bonding. So is that going to be attracted more to hexane that is nonpolar or water? Water. Okay. If we were to draw a particulate diagram, this would be a positive end here. So that means that the water would orient itself like this. Okay, because this is going to be my positive end is going to be here. the electron's going to want to stay on this side and pull away from the hydrogen. So this end is going to be positive. This end is going to be negative. It's going to be attracted to that negative end of the water molecule. So you want to make sure that you draw in that LDF and have the water oriented correctly. Okay. And then you got a few more of these. You can look up the answer keys for these tonight. I want 3, 7, and 3, 8 done tonight. Okay.
I